Stand in the absolute silence of a desert night and look up. Above you, thousands of stars burn like diamond dust against the velvet black. It feels full, it feels massive. You see the glowing bands of the galaxy, the wandering planets, the ancient constellations that have guided sailors for millennia. You feel small beneath the weight of all that visible light. But here is the terrifying truth. It is a lie. Everything you can see, every star, every cloud of gas, every planet, every face you have ever loved, is nothing more than a thin coat of paint on a massive, invisible wall. You are standing in a room that is pitch black, thinking you see the whole world, when in reality, you are only seeing the tiny sparks that happen to catch the light. The rest of the universe is hiding, it is watching, and it is holding us together. This is the story of the greatest ghost hunt in human history. It is a story not about what we found, but about what we could not find. For thousands of years, we believed that if we could touch it, see it, or weigh it, it was real. We thought the universe was made of earth, air, fire, and water, or later, atoms, protons, and electrons. We were arrogant. We assumed that our eyes were capable of seeing the whole picture. But the cosmos has a secret so vast that it accounts for nearly everything in existence. Without this invisible hand, your body would not hold together, the sun would not burn, the galaxy would fly apart like a broken wheel. We call it dark matter, but a better name might be the silent architect. It is the ghost in the machine. And to find it, we have to go back to a time when the universe felt much smaller and much safer. The year is 1933. The location is the Obsidian Peak Observatory, a lonely fortress of science perched high above the clouds in California. The air up here is thin and biting cold. The wind howls around the metal dome, rattling the shutters, trying to break the concentration of the man inside. His name is Dr. Elias Thorne. He is not a man who makes friends easily. He is brilliant, abrasive, and difficult. A man who prefers the company of galaxies to the company of people. While the rest of the world is worrying about economics and impending war, Thorne is worried about something much bigger. He is staring into the heart of the Æthelgard cluster, a swarm of over 1,000 galaxies drifting in the deep dark, millions of light years away. Thorne adjusts the heavy iron wheels of the telescope. The gears groan in the cold. He is trying to do something that seems simple on paper, but is excruciatingly difficult in practice. He wants to weigh the universe. He wants to know how heavy that cluster of galaxies really is. To do this, he uses a clever trick of light. He knows that gravity acts like a leash. If a galaxy is heavy, its gravity pulls hard. If it pulls hard, the things orbiting it must move fast to keep from falling in. It is the same reason a race car sticks to a banked track. Speed fights gravity. By measuring the speed of the galaxies swirling around the center of the cluster, Thorne believes he can calculate the mass of the entire system. He captures the light from the Æthelgard cluster on glass photographic plates. He spends shivering nights guiding the telescope, fighting the drift, making sure the photons from deep space etch their tiny signatures onto the emulsion. Then, he takes the plates to his desk. The room is silent, except for the scratching of his pencil and the ticking of a clock. He measures the shift in the light, the cosmic stretch. When an object moves away from us, its light stretches out, turning red. When it moves toward us, it squashes, turning blue. By measuring this shift, Thorne can tell exactly how fast those galaxies are moving. He runs the numbers, he stops, he cleans his glasses, frowns, and runs the numbers again.
Could that affect
the silence in the observatory deepens. The math does not make sense. According to the light he can see, the combined glow of billions of stars in those 1,000 galaxies, the cluster should have a certain amount of gravity, a specific weight. That gravity should be strong enough to hold the galaxies in orbit at a leisurely pace. But the galaxies in the Æthelgard cluster are not moving leisurely. They are screaming through the void. They are moving at thousands of miles per second. Thorne stares at the paper. His heart beats a little faster. At these speeds, the cluster should not exist. The visible gravity is far too weak to hold on to galaxies moving that fast. They should have flung themselves apart billions of years ago. They should be scattering into the darkness like shrapnel from an explosion. But they are not. They are staying together. They are locked in a tight, graceful dance. It is impossible. It is like watching a car spin around a racetrack at 1,000,000 miles an hour without skidding off. There is no way the tires or the gravity should hold. Unless there is something else there. Thorne looks back at the photograph of the cluster. He sees the fuzzy blobs of light that represent entire civilizations, entire histories. And he realizes that what he is seeing is a deception. The visible stars are just the debris floating on top of something much, much deeper. He calculates how much gravity would be needed to hold the cluster together at those speeds. The answer is staggering. To keep the Æthelgard cluster intact, there must be 400 times more mass than what can be seen in the stars. 400 times. Imagine looking at an elephant and realizing that what you see is only the skin, and inside, hidden from view, is a mountain of lead. He calls it the shadow mass. He writes down his findings. He proposes that the universe is filled with a mysterious, invisible substance that has no light, no reflection, and no heat, but carries immense weight. He suggests that the galaxies we see are just glowing specks caught in the gravity of these massive, invisible clouds. It is a radical, terrifying idea. It implies that we are blind. It implies that the majority of the universe is made of stuff we cannot even imagine. Thorne publishes his work. He expects shock. He expects debate. He expects the scientific community to rush to their telescopes to confirm the existence of this shadow mass. Instead, he gets silence. And then, he gets ridicule. The idea is too big, too strange. The astronomers of the time are comfortable with what they can see. They have just gotten used to the idea that other galaxies exist. Now this grumpy man on a mountain wants to tell them that those galaxies are mostly ghosts? It is too much. They dismiss him. They say he made a mistake. They say he overestimated the speeds or underestimated the brightness of the gas. They say the shadow mass is a fantasy. Thorne eventually moves on to other mysteries. The plates of the Æthelgard cluster are filed away in a dusty cabinet. The concept of the invisible universe is buried. For nearly 40 years, the ghost waits. The galaxies keep spinning too fast. The clusters keep holding together when they should be flying apart. The evidence is right there, written across the sky in giant, invisible letters, but nobody is willing to read it. We went back to sleep, content with our 5% universe. We thought we had solved the puzzle. But gravity is patient. Gravity does not care about human belief or scientific fashion. Gravity pulls, whether we acknowledge it or not. And in the 1970s, a new pair of eyes would look up at the night sky, not at a distant cluster this time, but at the galaxies right next door. These eyes belong to a woman who was used to being ignored, used to fighting for her place in the dark, and she would see something that could not be buried in a cabinet. She would see that the ghost was not just far away in the Æthelgard cluster. She would find it in our own backyard. Part 2. The years drifted by like dust in a sunbeam. The files on the shadow mass gathered yellow stains in the back of academic cabinets, ignored and forgotten. The world had moved on. Science had split the atom, landed men on the moon, and built telescopes that could peer into the very edge of time. But the ghost was still there, waiting in the dark. It waited until 1970, in the quiet corridors of the Meridian Institute in Washington, D.C., where a woman named Dr. Lena Voss was looking for a sanctuary. Voss was an outsider. In a field dominated by men who smoked pipes and slapped each other on the back in clubrooms she wasn't allowed to enter, she had to fight for every inch of telescope time. She had been rejected from top universities, not because she lacked the mind, but because she lacked the right gender. She was told the observatories had no facilities for women, as if a restroom were a more complex engineering challenge than a telescope. But Voss did not care about the politics of the ground. She cared about the sky. She wanted a project that was quiet, something the loud voices in the room weren't fighting over. She wanted to study the gentle, spinning dance of spiral galaxies. She teamed up with a man named Silas Kane. Kane was not a theorist. He was a builder. He was a master of glass and metal, a man who could build an eye capable of seeing things no human had ever seen. Together, they built a new kind of spectrograph. It was a machine that didn't just take pictures of stars. It dissected their light. It sliced the glow of a galaxy into a rainbow, revealing the chemical fingerprints and, more importantly, the speed of the stars. It was a cosmic speedometer. They turned their new electronic eye toward our nearest neighbor, the Helix Galaxy. The Helix is a monster. It is a swirling island of 1 trillion stars, a majestic pinwheel glowing in the deep night, 2.5 million light-years away. It is so close that on a dark night you can see its fuzzy core with your naked eye. Voss and Kane wanted to map exactly how it moved. They wanted to see how the stars orbited the center. The physics seemed simple. It should have been like watching a merry-go-round, or our own solar system. Think of the solar system. The sun sits in the middle, holding 99% of the mass. Mercury, the closest planet, screams around its orbit at over 100,000 miles per hour to keep from falling in. But way out at the edge, lonely Neptune creeps along at a sluggish 12,000 miles per hour. The rule was absolute. The farther you are from the heavy center, the slower you move. Gravity gets weaker with distance. It fades. Voss expected the Helix Galaxy to follow the same rule. The bright center was where all the stars were. The outer edges were thin, wispy, filled with dark gas and scattered suns. The stars out there in the suburbs of the galaxy should have been drifting slowly, barely holding on. It is a cold night in Arizona. The dome of the observatory is open to the vacuum. Voss sits in the cage at the base of the telescope, wrapped in a heavy coat, watching the monitors. The silence is heavy. The only sound is the hum of the tracking motors and the scratch of a stylus on a chart recorder. Kane is adjusting the voltage. They pick a star at the very edge of the helix, a lonely sentinel facing the empty void. The data comes in. The stylus twitches. Voss looks at the line. She frowns. The line is flat. She checks the calibration. She assumes the machine is broken. The star at the edge isn't moving slowly. It is moving fast. In fact, it is moving just as fast as the stars near the core. She moves the telescope to another star, even farther out. The result is the same. She pushes the instrument to the absolute limit, measuring invisible gas clouds way out in the darkness, far beyond the visible spiral arms. They should be crawling. They should be barely moving. But they are racing. The stylus scratches out a flat line across the paper. It defies Newton. It defies Kepler. It defies Einstein. According to the laws of physics, those outer stars are moving so fast that they should be flung off into deep space. The galaxy should be ripping itself apart. It should be spraying stars into the dark like water flying off a spinning bicycle wheel. There is not enough visible gravity to hold them. The Helix Galaxy is a dinner plate spinning at 1,000 miles an hour, and yet, not a single crumb is falling off. Voss feels a chill that has nothing to do with the night air. She realizes she is looking at a violation of reality, or she is looking at the ghost again. She remembers the old, ridiculed papers of Elias Thorne, the Shadow Mass. For weeks, Voss and Kane work in secret. They test another galaxy, then another, then 10 more. They look at tight spirals, loose spirals, broken spirals. The answer is always the same. Every single galaxy is spinning too fast. The rotation curves are all flat. The universe is playing a trick. Voss sits in her office, surrounded by stacks of graph paper. Each sheet represents a galaxy, and each line represents an impossibility. She realizes the magnitude of what she has found. It isn't just a quirky cluster far away. It is everything. It is everywhere. The visible galaxy, the beautiful glowing spiral we see in photographs, is just the tip of the iceberg. Imagine looking at the ocean at night. You see the white foam of the waves glowing in the moonlight. You might think the foam is the ocean, but the foam is just a tiny, frothy layer on top. Beneath it lies miles of dark, heavy, unseen water. Voss realizes that galaxies are the same. The stars are just the foam. The galaxy is actually a massive, invisible sphere of shadow mass, and the stars are just stuck in the middle of it. She realizes that the dark matter isn't just out there, it is the container. We are living inside a bubble of invisible cement. Voss publishes her findings. This time, the silence is different. It isn't the silence of dismissal. It is the silence of fear. The data is too clean to ignore. The instruments are too precise to mock. The scientific community looks at her flat lines, and the realization ripples through the halls of academia like a tremor. The floor has dropped out from under them. They had spent centuries mapping the stars, thinking they were mapping the universe. Now, Dr. Lena Voss has shown them that for every ounce of star stuff they can see, there are 5 ounces of something else, something invisible. Something that doesn't glow, doesn't reflect, doesn't shadow. It passes through walls. It passes through planets. But the question remains, what is it? Is it just dead stars, black holes, rocks, or is it something much stranger? As the 1980s dawn, the panic sets in. The theorists rush to their chalkboards. They try to save the old universe. They propose that the shadow mass is just dark normal matter, planets drifting in the void, or burnt-out suns. They call them machos, massive compact halo objects. It is a comforting thought. It means the universe is still made of the same stuff, protons, neutrons, atoms, just hard to see. But the universe is rarely comforting. And deep in the calculations of the Big Bang, a new problem is rising. The numbers for normal matter are capped. There physically isn't enough normal stuff in the cosmos to account for all this gravity. If it's not protons and it's not atoms, then what is holding the stars? The mystery shifts from the telescope to the particle accelerator. The answer isn't in the sky anymore. It is in the very fabric of reality. And to find it, we will have to look at how the universe began, and how the invisible hand shaped the very first light of creation. The ghost was about to get a name, and the hunt was about to go underground. The realization hit the scientific world like a rogue wave. The universe was not what we thought it was. For centuries we had stared at the night sky and believed we were looking at the main event. We thought the stars were the actors, the galaxies were the stage, and the darkness was just empty space. But Dr. Lena Voss's flat lines on the graph paper told a different story. The darkness was not empty. The darkness was the stage, the actors, and the script. The stars were just the stage lights, turning on to show us where the furniture was hidden. By the early 1980s, the unease had settled deep into the bones of cosmology. The idea of the shadow mass, now officially branded dark matter, was no longer a fringe theory from a grumpy man on a mountain. It was a crisis. It was a gaping hole in our understanding of reality. If 85% of the matter in the universe was invisible, then physics was essentially studying the dust on the window pane while ignoring the mountain outside. Scientists began to race toward a new question. If this stuff is everywhere, what is it doing? It isn't just holding individual galaxies together like invisible glue. Its influence had to be bigger. It had to be cosmic. They turned to the most powerful tool they had, the supercomputer. In cold, climate-controlled rooms, deep in the basements of universities, immense machines began to hum. They were fed the laws of gravity, the physics of gas, and the history of the Big Bang. The goal was to run a simulation called the Genesis Code. They wanted to recreate the birth of the universe inside a silicon chip. They ran the simulation with only ordinary matter. The atoms, the protons, the stuff we can see. They hit run and watched billions of years of cosmic history flash by in seconds. The result was a disaster. In the simulation, the universe remained a smooth, hot soup. The gas refused to clump. The gravity of ordinary matter was too weak, and the expansion of the universe was too fast. The gas just spread out, thin and useless. No galaxies formed, no stars ignited, no planets cooled. The screen showed a dead, dark universe, a void without life. Then they changed the code. They added the ghost. They programmed in the dark matter, massive, slow-moving, invisible. They gave it 5 times the weight of the ordinary gas. They hit run again. This time, the screen exploded with structure. The dark matter didn't feel the pressure of light or heat. It just felt gravity. It collapsed instantly, forming deep, invisible wells. The ordinary gas, attracted by this massive gravity, flowed into these wells like water running down a drain. It pooled, it compressed, and then ignited. Stars flickered on. Galaxies spun into existence. They clustered together along vast, invisible filaments, forming a giant, glowing spiderweb across the digital cosmos. The simulation matched the real sky perfectly. The computer had proven something profound. Dark matter was not just a cosmic glue holding spinning galaxies together. It was the seed. It was the skeleton. Without this invisible scaffolding, the universe would be a featureless fog. You would not be here. The iron in your blood, the calcium in your bones, the oxygen in your lungs, none of it would have forged in the hearts of stars, because the stars never would have formed. We owe our existence to a ghost, but knowing what the ghost did was not the same as knowing what the ghost was. The hunt shifted from the telescope to the blackboard. What could be heavy, invisible, and everywhere? The first guess was the most comforting one. Scientists hoped it was just normal stuff that was hard to see. They called them machos, massive compact halo objects. The theory was simple. Maybe the galaxy is filled with billions of dead stars, black holes and rogue planets floating in the dark. Maybe the universe is just a dark room full of dark rocks. It made sense. It was safe. It didn't require new physics. So astronomers launched a massive surveillance operation. They stared at millions of stars in the Magellanic Clouds, waiting for a macho to drift in front of them. If a dark, dead star passed in front of a bright background star, its gravity would act like a lens, briefly magnifying the light. It would be a telltale flicker, a cosmic wink. They waited, they watched, they analyzed terabytes of data. They found a handful of brown dwarfs, a few lonely black holes. But nowhere near enough. It was like trying to explain the weight of the ocean by counting the fish. The math didn't work. Even if you counted every rock, every asteroid, and every dead star, it only added up to a fraction of the missing mass. The universe wasn't hiding normal matter. It was hiding something else. The realization was chilling. The dark matter was not made of protons. It was not made of neutrons. It was not made of atoms at all. It was a new form of matter entirely. A substance that had never been captured in a jar, never seen in a microscope, never created in a collider. It was a phantom particle. Physicists began to profile the suspect. They knew it had to be heavy, or massive, to create all that gravity. They knew it had to be weakly interacting, meaning it ignored light and magnetism completely. It could pass through a lead wall as if the wall wasn't there. It could pass through the Earth. It could pass through you. They called it the WIMP, the weakly interacting massive particle. But there was another clue, hidden in the speed. If the dark matter particles were light and fast, like neutrinos, they would zip around the universe at near light speed. They would wash out all the structure, erasing the cosmic web before it could form. This was called hot dark matter. The simulation said no. The universe we see is clumpy, organized, and structured. Therefore, the dark matter had to be slow. It had to be sluggish. It had to be cold. Cold dark matter became the leading theory. a universe filled with a slow, heavy, invisible fog that drifts through everything, silent and untouchable. Imagine the psychological weight of this. You are a scientist in the 1990s. You have realized that the periodic table of elements, that chart hanging in every chemistry classroom in the world, is just a list of the rare, exotic debris of the universe. The real matter, the main matter, is not on the chart. It is an alien substance that permeates the room you are sitting in right now. But a theory is just a story until you have proof. The WIMP was a great idea, but no one had ever seen one. The macho hunters had failed. The rotation curves were indirect evidence, like seeing footprints in the snow but never seeing the wolf. Skeptics began to rise. They asked a valid question. How do we know it's matter at all? Maybe we just don't understand gravity. They argued that perhaps Newton and Einstein were slightly wrong. Maybe gravity works differently on huge scales. Maybe there is no ghost. Maybe the laws of physics just change when you get far enough away from home. It was a seductive idea. It would solve the problem without inventing a magical invisible particle. The battle lines were drawn. On one side, the dark matter defenders. On the other, the gravity modification rebels. The scientific community was deadlocked. They needed a tiebreaker. They needed a smoking gun. They needed to see the ghost separate from the body. In the vast emptiness of space, nature was preparing to stage exactly that experiment. Two massive clusters of galaxies, titans of the deep universe, were on a collision course. They were rushing toward each other at millions of miles per hour. When they crashed, they would tear the sky apart. They would create a cosmic crime scene that would either prove the ghost existed or banish it forever. The telescope was pointed. The collision was ancient, the light just reaching us. The stage was set for the Titan collision, the moment where the invisible would finally be forced to show its face. Part 4. Deep in the southern constellation of Carina, nearly 4 billion light-years from Earth, a scene of unimaginable violence has been frozen in time. It is known officially as 1EO65758, but to those who study the hidden universe, it is known as the Bullet Cluster, or, for our story, the Titan collision. It is the most important crime scene in the history of astrophysics. It is the place where the universe finally slipped up and revealed its hand. To understand what happened there, you have to understand the anatomy of a galaxy cluster. It is not just a family of galaxies. It is a mixture of three things. First, you have the galaxies themselves, the stars, the planets, the light, which make up only about 1% or 2% of the mass. Second, you have the gas, huge burning clouds of hydrogen that fill the space between the galaxies. This gas is hot, heavy, and makes up about 12% of the mass. And third, you have the ghost, the dark matter, which makes up the vast majority, nearly 85% of the cluster. Usually these three things sit on top of each other, mixed together like ingredients in a cake. You cannot tell where the gas ends and the dark matter begins because they are occupying the same space. But in the Titan collision, nature decided to unmix the cake. Two massive galaxy clusters, each containing quadrillions of tons of matter, slammed into each other at a speed of 6 million miles per hour. It was a cosmic car crash on a scale that defies human comprehension. But because of the vast distances in space, the crash didn't happen in an instant. It took millions of years. And because it happened in slow motion, we can analyze the wreckage piece by piece. Here is what happens when galaxy clusters collide. First, the stars. Stars are incredibly small compared to the space between them. Even when two galaxies smash together, the stars almost never collide. They are like sand grains thrown through an open window. They miss each other completely. The stars from Cluster A passed right through the stars from Cluster B, continuing on their journey as if nothing had happened. Second, the gas. The gas clouds are different. They are huge, diffuse, and sticky. They create friction. Imagine throwing 2 buckets of water at each other in midair. The water slams together, splashes, heats up, and stops. That is what happened to the gas in the Titan collision. As the clusters merged, the gas clouds smashed into each other, creating a shockwave so intense it heated the hydrogen to 100 million degrees. The gas got stuck in the middle of the crash, glowing brightly in X-rays, screaming in the heat of the impact. Third, the dark matter. This was the moment of truth. If dark matter was just ordinary stuff hiding in the dark, rocks, planets, gas, it should have crashed and stuck in the middle, just like the visible gas. It should have felt the friction. It should have slowed down. But if dark matter was truly a ghost, a weakly interacting particle that ignores the laws of contact, it should behave differently. It should not feel friction. It should not feel the impact. It should pass right through the other cluster without slowing down, like a phantom walking through a wall. Astronomers turned their telescopes to the wreckage. They used X-ray telescopes to find the gas. There it was, glowing, angry red, piled up in the center of the collision, stopped dead by the friction. This was where the majority of the visible matter was. Then, they used gravitational lensing to find the mass. They looked at the background galaxies behind the collision. They measured how the light from those distant galaxies was being bent and warped. Remember, gravity bends light. The more mass there is, the more the light bends. By mapping the distortion, they could draw a map of where the heavy stuff actually was. The result was shocking. The map of the gravity did not match the map of the gas. The gas was stuck in the middle, but the gravity, the mass, was on the outside. The heavy, invisible stuff had kept going. It had passed right through the collision, exiting the other side, leaving the gas behind. The dark matter had separated from the ordinary matter. It was the smoking gun. It was the moment the ghost left the body. The Titan collision proved that dark matter is real. It proved that the invisible mass is not just a mathematical trick or a misunderstanding of gravity. If it were just modified gravity, the pull should have been centered on the gas, because that's where the visible mass is. But the pull was centered on empty space. The universe had been caught in a lie. The empty space was heavier than the glowing gas. This image, the blue lobes of invisible mass separating from the red knot of hot gas, became the most famous picture in modern cosmology. It silenced the skeptics. It drove a stake through the heart of the alternative theories. Gravity wasn't broken. The universe was just full of ghosts. With the reality of dark matter confirmed, the mood of the scientific community shifted. The time for debate was over. The time for the hunt had begun. We knew it was there. We knew it was heavy. We knew it was cold. We knew it could pass through solid matter without leaving a trace. But this presented a terrifying engineering challenge. How do you catch something that cannot be touched? How do you build a trap for a ghost? If you hold out your hand right now, billions of dark matter particles are passing through it every second. They are raining down on you from the sky, rising up through the floor, passing through your skull and your heart. They do not stop. They do not interact. To them, you are less than a shadow. You are not even there. To catch one, scientists realized they would have to get lucky. They theorized that occasionally, very, very occasionally, a dark matter particle might make a mistake. It might accidentally crash head-on into the nucleus of a normal atom. It would be a 1 in a trillion shot, a tiny, imperceptible nudge, a whisper of energy in a noisy room. But the surface of the Earth is too loud. We are constantly bombarded by cosmic rays, radiation from the sun, and the natural radioactivity of the air. Trying to hear the whisper of a dark matter particle on the surface is like trying to hear a pin drop at a heavy metal concert. It is impossible. So the physicists did the only thing they could do. They left the light behind. They packed up their sensitive instruments, their crystals, and their tanks of liquid gas, and they went down. They went into the deepest holes humanity has ever dug. They went into old gold mines in South Dakota, tunnels beneath mountains in Italy, and caverns in China. They descended thousands of feet into the crust of the Earth, using the billions of tons of rock above them as a shield to block out the noise of the universe. In the darkness of the underworld, they built their temples. They built machines of exquisite sensitivity, designed to wait for years, decades, just to catch a single flicker of light. They entered the era of the deep search. The ghost hunt had moved from the infinite sky to the claustrophobic dark, and down there, in the silence, the waiting began. The journey to the center of the mystery begins with a cage. It is a rattling industrial elevator shaft that drops you out of the sunlight and into the crust of the earth. You leave the wind, the birds, and the blue sky behind. The descent takes 10 minutes. The air pressure rises. The temperature of the rock climbs. You are traveling nearly a mile straight down, deeper than the height of the tallest skyscrapers, deeper than the graves of ancient kings. You are entering the deep hollow. This was once a gold mine. For a century, men tore the earth apart here, hunting for veins of yellow metal to make coins and jewelry. Now, the gold is gone, and the miners have been replaced by a new breed of prospector. They are not looking for wealth, they are looking for truth. They have turned these dark, dripping tunnels into the cleanest place on the planet. Step out of the elevator. The tunnel is lined with rough, black rock, but ahead, there is a door. You pass through an airlock, scrub your boots, and don a white suit. The air inside is filtered, scrubbed of every speck of dust. You have entered the sanctum. It is a cathedral of science buried in the dark, a sterile, white laboratory humming with power, surrounded by millions of tons of crushing granite. In the center of this cavern sits the machine. It does not look like a telescope, it looks like a thermos. A giant, gleaming cylinder of titanium and steel, wrapped in cables, suspended in a tank of ultra-pure water. This is the trap. This is the device built to catch the ghost. Inside the titanium walls lies the heart of the experiment, 10 tons of liquid xenon. Xenon is a noble gas, rare and expensive. It is heavy, dense, and incredibly aloof. It does not want to interact with anything. To keep it liquid, the machine must be cooled to minus 150 degrees. It is a freezing, silent pool of atoms sitting in absolute darkness, waiting. The logic of the trap is simple but desperate. The scientists know that dark matter is passing through the Earth right now. It drifts through the granite rock as if it were mist. It flows through the laboratory walls. It floods through the tank. Most of the particles, trillions upon trillions of them, will pass through the liquid xenon without touching a thing. They will exit the other side and continue their journey through the planet and back out into space. But the scientists are betting on a mistake. They are hoping that just once, maybe once a year, maybe once in a decade, a single dark matter particle will trip. It will crash head-on into the nucleus of a xenon atom. If that collision happens, the xenon atom will recoil. It will shudder, and in that moment of violence, it will release a tiny, microscopic flash of ultraviolet light. A single spark in the dark. Lining the walls of the tank are hundreds of electronic eyes, photomultiplier tubes. They are the most sensitive light detectors ever built. They can see a single photon. They are staring into the black liquid, unblinking, 24 hours a day, watching for that one, solitary spark. It sounds straightforward, but in practice, it is a nightmare of paranoia. The problem is that the universe is noisy. The surface of the Earth is screaming with radiation. Cosmic rays from exploding stars bombard us constantly. If you put this detector on the surface, the xenon would light up like a Christmas tree. The cosmic rays would trigger the sensors 1,000,000 times a second. You would never find the dark matter signal in the chaos. That is why they dug the hole. The mile of rock above their heads acts as a shield. It blocks the cosmic rain. It creates a zone of silence. But even down here, the silence is not perfect. The rock itself is radioactive. It contains trace amounts of uranium and thorium that decay and spit out particles. The steel of the tank, the glass of the sensors, even the air in the room, everything is slightly radioactive. To a machine this sensitive, a banana is a nuclear bomb. The dust on a scientist's shoulder is a roaring fire. So the paranoia begins. The xenon must be purified, distilled over and over again, until it is the purest substance on Earth. The titanium for the tank is sourced from special foundries and tested for years. The water shielding the tank is cleaner than any mountain spring. The scientists have to build a Russian nesting doll of shields. lead, copper, polyethylene, water, layer after layer to block out the noise of the ordinary world. They are trying to create a place where absolutely nothing happens, a place of perfect atomic stillness. Because only in perfect stillness can you hear the whisper of the ghost. Imagine the tension in the control room. The scientists sit in front of banks of monitors. They watch the data scroll by. Most of the time, the screen is dark. Sometimes, a jagged line appears. A background event. A stray neutron from the rock. A bit of krypton gas that slipped through the filters. They analyze it, tag it, and discard it. It's just noise. They are waiting for a specific signature, a specific ratio of light to electrical charge that screams dark matter. Days turn into weeks. Weeks turn into months. The machine hums. The pumps cycle. The xenon sits there, cold and heavy. The scientists rotate shifts, drinking coffee, checking the diagnostics, staring at the flat lines. They are fishing in an invisible ocean, and the fish are refusing to bite. There is a psychological toll to this kind of science. It is not like the movies. There are no sparks flying, no countdown clocks, no frantic typing. There is only the long, oppressive wait. You start to question everything. Is the machine working? Is the calibration right? Did we miss a connection? Or, the darker thought, is there anything out there at all? What if the ghost is too ghostly? What if dark matter interacts so weakly that it will never touch a xenon atom, not in a million years? What if we have built the most expensive, most sophisticated hearing aid in history, and the universe is simply mute? But they cannot stop. The stakes are too high. If they see that flash, if they catch that particle, it changes everything. It would be the first time humanity has ever touched the other universe. It would win the Nobel Prize. It would rewrite the textbooks. It would tell us what we are actually made of. So they wait. They build bigger tanks. They get more xenon. They go deeper. In Italy, under the Gran Sasso Mountain, another team is doing the same thing. In China, deep under the Jingping Mountains, another tank waits. It is a silent race. A global competition to see who can be the most quiet, who can be the most patient. But as the years of the deep search dragged on, a new anxiety began to creep into the underground labs. The detectors were getting better. They were becoming thousands of times more sensitive than the first prototypes. They were ruling out the easy versions of dark matter. The imp that favored theoretical particle was running out of places to hide. The silence was becoming deafening. The lack of a signal was becoming a signal in itself. The ghost wasn't just elusive, it was taunting them. And while the physicists sat in their caves, watching the empty screens, the theorists on the surface began to whisper. They began to wonder if we were looking for the wrong thing entirely. Maybe the ghost wasn't a heavy, clunky particle crashing into atoms. Maybe it was something lighter. Something wavier. Something that sang a different song. As the tanks of xenon remained dark, the search began to branch out. It was time to tune the radio to a different station. It was time to look for the axion. The silence of the xenon tanks was a heavy burden. Year after year, the scientists in the deep underground stared at their data, hoping for a collision, a spark, a sign. But the WIMP, the heavy tank-like particle they had bet their careers on, refused to show up. As the detectors grew more sensitive and the results remained empty, a quiet anxiety began to spread through the physics community. It was the anxiety of the fisherman who has cast his net into the most promising waters, waited for hours, and pulled it up dry. What if we were fishing for the wrong fish? What if dark matter isn't a bowling ball crashing through the dark? What if it is something far more subtle? What if it is not a heavy rock, but a whisper? From the back of the theoretical library, an old idea was dusted off. It was a concept born in the 1970s, named after a brand of laundry detergent because it was designed to clean up a messy problem in nuclear physics. They called it the axion. To understand the axion, you have to completely change the way you think about matter. Forget the idea of particles as tiny bullets or billiard balls. The axion is different. It is a ghost among ghosts. It is theorized to be incredibly light, trillions of times lighter than an electron. It is so light that it barely has a physical presence at all. If WIMPs are like rocks thrown into a pond, axions are the water itself. The theory suggests that these particles are not rare. They are not drifting through space one by one. They are everywhere. They are packed together so tightly that they overlap, acting less like individual particles and more like a continuous wave. A field. A cosmic ocean. If this theory is true, you are not just being bombarded by dark matter, you are drowning in it. You are walking through a thick, invisible fluid that permeates every inch of space. It is vibrating inside your body. It is flowing through the walls. It is a background hum that has been playing since the beginning of time, but our ears are deaf to the frequency. The hunt for the axion requires a completely different kind of trap. You cannot catch a wave with a bucket of liquid xenon. You cannot wait for it to crash into an atom, because it is too light to cause a recoil. It would be like trying to knock down a building by throwing a feather at it. To catch an axion, you don't need a shield, you need a radio. The scientists moved from the deep mines to slightly shallower laboratories. They built a machine called the resonator. It does not look like the xenon tanks. It looks like a steampunk artifact, a beautiful, gleaming cylinder of copper and gold, lowered into a vat of liquid helium to cool it to near absolute zero. The science behind it is like magic. Theoretical physics predicts that if an axion flies through a strong magnetic field, it can spontaneously transform. It can stop being a ghost and turn into a photon, a particle of light, specifically a microwave photon. So the resonator is essentially a giant, supercooled magnet wrapped around a high-tech listening box. The scientists turn on the magnet, creating a field hundreds of thousands of times stronger than the Earth's. Then, they insert a copper rod, a tuning fork, into the chamber. And they listen. They are listening for a radio signal from the dark. They are waiting for the axions flowing through the magnet to convert into microwaves and make the copper cavity ring like a bell. But there is a catch. A massive, heartbreaking catch. To hear the signal, you have to be tuned to exactly the right frequency. The frequency depends on the mass of the axion, and nobody knows what the mass is. Imagine you are locked in a room with a radio. You know that somewhere on the dial, there is a broadcast that explains the secret of the universe. But the dial has millions of channels. You have to turn the knob one tiny fraction of a millimeter at a time. Listen for a few minutes, hear nothing but static, and then turn it again. This is the life of the axion hunters. They sit in the control room, watching the frequency graph. They tune the resonator to a specific pitch. They wait. They listen to the hiss of electronic noise. Nothing. They mark that frequency as empty on the map, and they turn the dial. It is a slow, agonizing scan. They are searching for a needle in a haystack, but the haystack is infinite, and the needle might be invisible. The atmosphere in these labs is different from the xenon mines. It feels less like a vigil and more like a sweep. There is a sense of rhythmic persistence. Tune, listen, scan, tune, listen, scan. They are sweeping through the radio spectrum of reality, hoping to stumble upon the station that is broadcasting the cosmic truth. If they find it, if the static suddenly spikes into a clear, sharp tone, it will be a moment of absolute transformation. It would mean that the universe is not silent. It would mean that space is filled with a choir, singing a single note that holds the galaxies together. But so far, the radio is silent. The scan continues, day after day, year after year. The scientists check the quote-unquote authorized frequencies, the ones predicted by the most popular theories. Nothing. They widen the search. They build newer, faster tuners. They look at higher pitches, lower pitches. They are searching the dark for a hum that might be too quiet to hear. And while the particle physicists are tuning their radios and staring into their tanks, the astronomers are trying a different approach. They are tired of waiting for the ghost to come to Earth. They want to go out and find it in the wild. They are building a new generation of eyes. Not just telescopes that take pictures, but machines that map the distortion of space itself. They want to create a 3D atlas of the invisible. Because out there in the deep void, dark matter is doing something strange. It is not just holding galaxies together, it is eating them, it is shredding them. It is leaving a trail of crumbs that we can follow. High above the atmosphere, a new space telescope is unfolding its solar wings. It is designed to stare into the blackest parts of the sky, where there seems to be nothing at all. It is looking for the weak lensing, the tiny, almost imperceptible warping of background galaxies. The goal is to map the skeleton of the cosmos. If you could strip away the stars, what would the universe look like? The simulations say it would look like a web. A vast, three-dimensional sponge made of dark matter filaments. Thick ropes of invisible mass stretching for hundreds of millions of light years, connecting giant knots where galaxy clusters live. We are about to try to see this web for the first time. We are going to try to photograph the invisible scaffolding. The camera lens opens. The light from a billion years ago hits the sensors, and as the data begins to flow back to Earth, we prepare to see the true face of our home. We are not living in a random scattering of stars. We are living in a trap. A beautiful, massive, inescapable web that has been growing in the dark since the beginning of time. And in the center of that web, lurking in the hearts of the galaxies, lies another mystery, a connection between the dark matter and the monsters that eat light. The black holes. Could they be related? Could the ghost and the monster be the same thing? In the catalog of cosmic terrors, nothing captures the human imagination like the black hole. It is the ultimate monster. A region of space where gravity is so intense that reality itself snaps. Light cannot escape. Time stops. It is a hole in the fabric of the universe, a drain down which matter flows and never returns. We usually think of black holes as the corpses of dead stars. A massive sun burns through its fuel, collapses under its own weight, and crushes itself into a singularity. But there is another kind of black hole. A theoretical kind. A black hole that was never a star. A black hole that has no right to exist, yet might be the answer to everything. We call them primordial black holes. To understand them, you have to go back to the very beginning. Before the first galaxy spun. Before the first star ignited. Before the first atom even cooled. Go back to the first fraction of a second after the Big Bang. The infant universe was not a quiet place. It was a boiling, screaming soup of energy. It was a chaotic storm of density and heat, expanding outward at impossible speeds. In this violent epoch, the soup wasn't perfectly smooth. There were ripples, tiny pockets where the energy was slightly denser than the surroundings. If one of these pockets was dense enough, gravity would have taken over instantly. It would have crushed that pocket of energy directly into a black hole. No star required. No burning, no fusion, no supernova. Just a direct collapse from the chaos of creation into a permanent scar on space-time. These are the primordial black holes, the fossils of the Big Bang. The theory suggests that the universe might be filled with them. They could be anywhere. And they could be any size. Some might be as massive as 1,000 suns. Others might be as small as an atom, but with the mass of a mountain compressed inside.
But what about the localized
Here is why this matters to our ghost hunt. Think about what a primordial black hole is. It creates gravity. It is invisible. It does not reflect light. It passes through galaxies without crashing. It matches the description of dark matter perfectly. What if the ghost isn't a particle at all? What if we have been building xenon tanks and radio resonators to catch a WIMP or an axion, when we should have been looking for swarms of tiny ancient black holes? For decades, this theory was dismissed. The math suggested that if these things existed, we would have seen them. The small ones should have evaporated by now, dissolving into radiation. The big ones should have messed up the orbits of stars. It felt like a dead end. But in 2015, the universe whispered again. Two massive black holes collided 1 billion light-years away. They merged with such violence that they shook the fabric of space-time itself. A machine on Earth, the gravitational wave observatory, felt the tremor. It heard the chirp of the merger. But there was something strange about these black holes. They were too heavy. They were much bigger than the black holes usually made by dying stars. They didn't fit the standard model. Astronomers looked at the data and asked a dangerous question. What if these weren't dead stars? What if they were the ancient ones? The door to the primordial black hole theory creaked open. Suddenly, the idea that dark matter might be composed of billions of these tiny dark objects wasn't so crazy. Imagine the halo of our galaxy, not as a cloud of particles, but as a swarm of silent, invisible holes, buzzing around us like gnats, their combined gravity holding the Milky Way together. It is a disturbing thought. It means we are swimming in a sea of tiny monsters. But whether dark matter is made of particles or black holes, its greatest work is not local. Its greatest work is the architecture of the cosmos itself. To see it, you have to pull back, way back. You have to leave the Earth, leave the solar system, leave the Milky Way. You have to float in the intergalactic void and look at the universe as a whole. When we map the positions of millions of galaxies, we do not see a random scatter of dust. We see a pattern. We see a structure so vast, it defies belief. It looks like a sponge. It looks like the neurons of a brain. It looks like a spider web. We call it the cosmic web. This is the skeleton of the universe, and it is made of dark matter. Huge invisible filaments stretch across the dark for hundreds of millions of light years. They are thick ropes of gravity, and flowing along these ropes, like dewdrops on a spider's silk, are the galaxies. The visible universe is just the decoration. The galaxies are drawn to the dark matter filaments because that is where the gravity is. They cluster at the intersections, the nodes of the web, creating massive cities of thousands of galaxies. Between the filaments there are the voids. The voids are the terrifying empty spaces of the universe, bubbles of nothingness that span billions of light years. Inside a void, there is almost no dark matter, and therefore almost no galaxies, just deep, absolute cold. If you were floating in the center of the Boots void, nearly 700 million light-years of emptiness would surround you. You would look out and see nothing. No stars, no galaxies, just an endless, suffocating black. You would be in the loneliest place in existence. But the cosmic web tells us something profound. It tells us that the universe grew up. We have computer simulations now that can replay the history of the cosmos. We start with a smooth, baby universe. We sprinkle in the dark matter. We hit play. We watch gravity do its work. We watch the dark matter collapse into strands. We watch the strands thicken. We watch the ordinary gas fall into the strands and light up as stars. We watch the voids grow empty as gravity sucks them dry. The simulation matches the reality perfectly. The web we see in the telescope is exactly the web the computer builds. This confirms the role of the ghost. Dark matter is the sculptor. It chiseled the universe out of the raw stone of the Big Bang. It decided where the galaxies would live and where the voids would grow. It built the house we live in. But there is a flaw in the map, a crack in the theory. When we look at the giant scale, the billions of light years, the model works perfectly. The web is there. The math is beautiful. But when we zoom in, when we look at the small scale, things get messy. We look at our own neighborhood. We look at the dwarf galaxies spinning around the Milky Way. According to the simulations, there should be thousands of them. The dark matter halo around our galaxy should be lumpy, filled with hundreds of tiny clumps, each one hosting a tiny galaxy. But when we look with our telescopes, we don't see thousands, we see dozens. Where are the missing satellites? Where are the tiny galaxies that should be swarming around us? Is the simulation wrong? Is our understanding of the ghost flawed? Or are they there but they are totally dark? Maybe the dark matter clumps exist but they failed to catch enough gas to make stars. Maybe we are surrounded by hundreds of dark galaxies, invisible islands of mass that contain no light, no heat, no life, just pure, silent gravity, hovering in the dark just outside our door. We call this the missing satellite problem. It is one of the biggest headaches in modern astrophysics, and it hints that the ghost might have properties we haven't figured out yet. Maybe dark matter isn't cold and still. Maybe it's warm. Maybe it moves just fast enough to wipe out the small clumps, erasing the tiny galaxies before they can form. Or maybe the ghost interacts with itself. Imagine two dark matter particles crashing into each other. If they are truly ghosts, they should pass right through. But what if they bounce? What if they have their own secret forces? What if there is a dark electromagnetism or a dark nuclear force? This opens a door to a possibility that is equal parts thrilling and humbling. What if there is a dark sector? What if dark matter isn't just one boring particle? What if it is a whole periodic table of invisible stuff? Dark atoms, dark chemistry, dark stars. Could there be an entire shadow universe sharing the same space with us, completely invisible, interacting only through gravity? Could there be dark planets orbiting dark suns, with complex dark structures that we can never see, never touch, never know? We are walking through a room, thinking we are alone, but maybe the room is crowded. Maybe we are just the only ones glowing in the visible spectrum. The search is no longer just about finding a particle. It is about mapping the unknown continents of reality. And as we build better maps, we are starting to realize that the visible universe, the one we love, the one we live in, might just be the foam on the surface of a very deep, very dark ocean. And deep in that ocean, something else is pushing back. Because gravity isn't the only player in this game. While dark matter tries to pull the universe together, something else is trying to tear it apart. The ghost has an enemy. The universe is a battlefield. For billions of years, a silent war has been raging in the vacuum. It is a war between two titans, two invisible forces that are fighting for the soul of the cosmos. On one side, we have the ghost we know, dark matter. It is the builder. It is the gravity. It tries to pull everything together, to bind the galaxies into a tight, safe web, to create structure out of chaos. It wants a universe that is close, connected, and eternal. But it is losing. Because on the other side, there is an enemy that does not want to build. It wants to destroy. It wants to tear the web apart. It wants to push every galaxy away from every other galaxy until the universe is a cold, lonely, infinite void. We call this enemy dark energy. To understand the shock of this discovery, you have to understand how we thought the story would end. For most of the 20th century, physicists believed that gravity was the only game in town. The universe began with the Big Bang, a massive explosion that sent everything flying outward. But we assumed that gravity, the combined pull of all the stars, gas, and that massive amount of dark matter, would eventually act as a brake. Think of throwing a ball into the air. It flies up fast at first, but gravity grabs it. It slows down. Eventually, it stops and falls back to your hand. We thought the universe was the ball. We thought the expansion would slow down. Maybe, billions of years from now, it would stop entirely. Then, the big crunch would begin. The galaxies would fall back together, heating up, merging, until the universe collapsed back into a single point, perhaps to be born again. It was a poetic cycle, a breathing cosmos. But in 1998, two teams of astronomers decided to check the speedometer. They were rivals. One team was based in California, led by a meticulous strategist we will call Dr. Marcus Hale. The other was an international squad, the Southern Sky Group, led by the young and ambitious Dr. Ian Cross. They were in a race to measure the deceleration of the universe. They wanted to know exactly how much the dark matter was slowing things down. To do this, they needed a ruler that stretched across the cosmos. They needed a light that was exactly the same brightness no matter where it was, so that if it looked faint, they knew it was far away. They found it in a dying star. There is a specific kind of explosion called a Type 1a supernova. It happens when a white dwarf, a dense, dead cinder of a star, steals too much gas from a neighbor. When it hits a critical weight, it detonates. The physics of the explosion are so precise that every single one burns with almost exactly the same brightness. They are the standard candles of the universe, 60-watt light bulbs scattered through the dark. The plan was simple. Find these explosions in distant galaxies. Measure how bright they look to tell how far away they are. Then measure how much their light has been stretched by the expansion of the universe, the redshift, to tell how fast they are moving. If gravity was winning, the distant supernovae should be brighter than expected. They should be closer to us because the universe's expansion should have been slowing down over the last few billion years. The teams went to work. They used the biggest telescopes in Chile and Hawaii. They scanned the blackest patches of sky, night after night, waiting for a pixel to change. A supernova in a distant galaxy looks like nothing more than a faint dot that appears for a few weeks and then fades. It requires agonizing precision to catch one. Months passed. The data began to trickle in. The computers crunched the numbers. Dr. Hale sat in his office in Berkeley, staring at the plot on his screen. The data points were scattering across the graph. He checked the code. He checked the calibration. He assumed there was dust on the lens. He assumed the telescope was sagging. The data was wrong. It had to be wrong. According to the measurements, the distant supernovae were not brighter than expected. They were fainter, much fainter. This meant they were farther away than they should be. The universe wasn't slowing down. The ball wasn't falling back to Earth. The ball was flying upward, and somehow, miraculously, it had strapped on a rocket engine and was speeding up. The expansion of the universe was accelerating. Across the ocean, Dr. Cross and his team were seeing the same thing. The shock was absolute. It violated every intuition we had about physics. Gravity pulls. It attracts. It slows things down. There is no force in the standard model that pushes space apart. And yet, the galaxies were rushing away from us faster today than they were yesterday. The conclusion was inescapable. There was energy in the vacuum. Empty space was not empty. It was filled with a pressure, a repulsive force that grows stronger as the universe gets bigger. As space expands, it creates more vacuum, which creates more of this energy, which pushes the expansion even faster. It is a runaway feedback loop. They named it dark energy, and when they calculated how much of it was out there, the numbers were humbling. The universe is a pie. The visible matter, the stars, the gas, the planets, you, me, is a tiny slice, 5%. The dark matter, the invisible glue holding the galaxies together, is a bigger slice, 27%. But the rest, the dominant force? Dark energy makes up 68% of the universe. We are not just the minority, we are a rounding error. The universe is mostly made of a mysterious energy that is trying to rip it apart. This discovery changed the fate of the dark matter story. For billions of years, dark matter had been the hero. In the early universe, it was strong enough to pull the gas together and build the galaxies. It built the cosmic web. It created the safe harbors where life could evolve. But the war has turned. As the universe expands, the dark matter spreads out. Its gravity gets diluted. It gets weaker. But dark energy does not get diluted. It is a property of space itself. The more space you have, the more dark energy you have. About 5 billion years ago, roughly around the time our sun was being born, the balance of power shifted. Dark energy became stronger than the gravitational pull of the matter. The universe hit the gas pedal. The consequences are terrifying. It means the cosmic web is doomed. The dark matter filaments are being stretched. The knots are being pulled apart. Right now, the gravity of the dark matter is still strong enough to hold individual galaxy clusters together. The Milky Way and Andromeda are still locked in a dance and will eventually merge. But the distant clusters? They are leaving. Every second, a galaxy crosses the cosmic horizon, moving away from us faster than the speed of light. Its light will never reach us again. It has fallen off the edge of the observable world. The universe is emptying out. If this acceleration continues, billions of years from now, the sky will go dark. The other galaxies will be swept away into the void, too far to see. An astronomer born in that distant future would look up and see only the stars of our own galaxy. They would assume the Milky Way was the entire universe. They would have no way of knowing that a vast, rich web once existed. The evidence of the Big Bang, the evidence of the expansion, the evidence of the dark matter filaments, all of it will be erased by the darkness. We are living in a privileged time. We are living in the brief window of cosmic history where we can see the light from the neighbors before the lights go out. The discovery of dark energy earned the teams the Nobel Prize, but it left the physics community with a headache that has never gone away. We now have two dark mysteries instead of one. Dark matter, the invisible mass that pulls. Dark energy, the invisible force that pushes. They are total opposites, yet they conspire to create the universe we see. One builds the stage, the other expands the theater. And we are stuck in the middle, trying to figure out what either of them actually is. Because here is the cruelest joke of all. We don't know if they are connected. Are they two sides of the same coin? Is there a dark fluid that acts like matter when it's clumped and energy when it's spread out? Or are they completely unrelated phenomena, two strangers passing in the night? Some theorists have begun to wonder if our understanding of gravity is fundamentally broken. They look at the flat rotation curves of the galaxies, dark matter, and the accelerating expansion of the universe, dark energy, and they ask, what if there are no invisible particles? What if there is no invisible energy? What if Einstein's equation is just wrong? Quote, "It is a heresy." But when you are faced with a universe that is 95% invisible, heresy starts to look like a viable option. So the hunt splits. Half the scientists go deep underground to catch the dark matter particle. The other half look to the geometry of the universe, trying to crack the code of the acceleration. But there is one place where these two mysteries collide. One place where the gravity is so strong and the energy so intense that the laws of physics might just break down enough to show us the truth. We have to go back to the monster. We have to go back to the edge of the black hole. Because recently, we managed to do the impossible. We didn't just listen to a black hole. We didn't just theorize about it. We took a picture of one. In April 2019, the world stopped to look at a picture. It was a blurry, glowing orange ring surrounding a pitch-black center. It looked like a coal burning in a fire, or an eye staring back from the deep. It was the first image ever captured of a black hole, the supermassive monster at the heart of the galaxy, Messier 87, 55 million light-years away. To get that image, we had to turn the entire Earth into a telescope. We synchronized dishes in Antarctica, Spain, Hawaii, and Chile, linking them with atomic clocks so precise they would lose only a second every 100 million years. We peered into the heart of darkness, and we saw the shadow of the event horizon. It was a triumph of human engineering, but for the dark matter hunters, it was a moment of bittersweet clarity. The image proved that Einstein was right. Again, his theory of general relativity, written down in 1915 with nothing more than a pen and paper, perfectly predicted the shape of that orange ring. Gravity behaves exactly as the equations say it should, even in the most extreme environment in the universe. This makes the mystery of dark matter even more haunting. If gravity works perfectly at the edge of a black hole, and it works perfectly in our solar system, why does it fail in the space between? Why do the galaxies spin too fast? Why does the bullet cluster separate? The success of the black hole image closed the door on the easy answers. It suggests that our math isn't broken. The universe is just fuller than we thought. The ghost is real. It is still there, hiding in the gaps between the data points, refusing to step into the light. As we stand here today, nearly a century after Dr. Elias Thorne first noticed the impossible speeds of the Æthelgard cluster, we have to confront a difficult, emotional truth. We might not find it. We have built the most sensitive ears in history and heard only silence. We have built the deepest traps and caught nothing. We have mapped the invisible web, but we have never touched the silk. There is a very real possibility that dark matter belongs to a dark sector that interacts with us only through gravity. If that is true, we will never see a flash in a xenon tank. We will never hear a radio signal in a resonator. We will be like a person locked in a soundproof glass room, able to see the trees moving in the wind outside, but never able to feel the breeze. This is a humbling thought. For the last 400 years, since Galileo first pointed a telescope at Jupiter, the story of science has been a story of seeing more. We saw the moons, then the planets, then the stars, then the galaxies, then the microwave background of the Big Bang. We assumed that if we just built a bigger eye, we would see everything. Dark matter is the wall we have hit. It is the universe telling us, you are not allowed to see this. But in that silence, there is a profound beauty. Think about what dark matter means for you. It means that the universe is not a cold, empty void with a few scattered stars. It is a dense, rich ocean. You are not separated from the distant galaxies by nothingness. You are connected to them by a vast, invisible landscape of mass. The space between us is alive with gravity. It means that we are the anomaly. We used to think we were the normal ones. We thought that matter made of protons, neutrons, and electrons, the stuff of rocks, water, and flesh, was the standard building block of reality. But the numbers tell us we are the rare, exotic exceptions. The universe is 95% dark energy and dark matter. We, the visible, glowing, solid matter, are the foam. We are the glitter. We are the 5%. To a dark matter alien, we would be the ghosts. We would be the shimmering, unstable phantoms that glow for a brief cosmic moment and then fade away, while the dark matter endures forever. This shift in perspective is the true legacy of the dark matter hunt. It is the final death of our ego. First, we learned we weren't the center of the solar system. Then, we learned we weren't the center of the galaxy. Then, we learned our galaxy was just one of billions. And now, we have learned that we aren't even made of the main stuff of the universe. We are a minority in our own home. But what a beautiful minority we are, because we are the only part of the universe that glows. We are the only part that can reflect light. We are the only part that can build eyes to look back at the dark. The search for dark matter is not a failure because we haven't found a particle. It is a triumph because we realized it was there at all. Imagine the intelligence required to look at a spinning galaxy and say, there is something missing. Imagine the audacity to weigh the invisible. The hunt has pushed our technology to the absolute limit. It has forced us to dig miles into the Earth and launch telescopes millions of miles into space. It has united thousands of scientists across generations and borders in a shared quest for truth. And perhaps the mystery is the point. If we knew everything, if we had a complete list of every particle and every force, and we could write the equation of the universe on a t-shirt, the magic would fade. The cosmos would become a solved puzzle, a finished book to be put on a shelf. But dark matter ensures that the book remains open. It ensures that the night sky remains a place of wonder. When you look up, you are not just seeing the stars. You are looking into the face of a giant. A giant that holds the Milky Way in its palm, that guided the gas to form the sun, that anchored the Earth so that life could begin. The dark matter is the silent guardian. It is the womb of the galaxies. Without it, the universe would be a thin, cold mist, forever expanding, forever dark. It crushed the gas together to light the first fires. It built the structure that allowed us to exist. So even if we never catch the particle, we know the ghost is there. We feel its hand every time we look at the Milky Way. We see its artwork in the cosmic web. We owe it our lives. The story of dark matter is not a detective story where we catch the killer in the last act. It is a love story. It is the story of a tiny, fragile species of light lovers trying to understand the dark ocean that holds them. We are the conscious part of the universe. We are the way the cosmos thinks about itself. And for now, the cosmos is thinking, there is more. The tanks in the deep mines are still humming. The telescopes in the high desert are still slewing across the sky. The theorists are still scribbling on their whiteboards, dreaming of axions and black holes and extra dimensions. The hunt goes on. And maybe, just maybe, tomorrow, the signal will come. A flash of light in the liquid xenon, a ring of a copper bell, a sudden clarity in the data. But until that day comes, we stand on the shore of the invisible, watching the waves roll in from the deep, knowing that the water goes on forever. We are small, we are rare, but we are awake, and we are looking into the dark with our eyes wide open. This is the portrait of the invisible universe. If you were to take everything we have learned, every observation from the mountaintops of California, every flash of data from the mines of South Dakota, every pixel captured by our telescopes in orbit, and compress it into a single image, what would you see? You would not see the universe you recognize. You would not see a sky filled with twinkling stars and spiraling galaxies. You would see a vast, dark ocean. A turbulent, heaving sea of shadow that stretches for 93 billion light-years. And floating in that ocean, rare and fragile, are tiny islands of light. That is us. That is the 5%. The story we have just traced is not merely a collection of scientific facts. It is a chronicle of human realization. It is the story of how we woke up. Remember the speed. That was the first crack in the illusion. Dr. Illis Thorne standing in the freezing dome, realizing the galaxies were moving too fast to make sense. Dr. Lena Voss watching the flat lines on her chart recorder, proving that the outer edges of the spiral were spinning just as fast as the core. These were not errors. They were the speedometer of the cosmos telling us that the engine was bigger than the car. Remember the collision, the Titan, the moment nature smashed two clusters together to prove a point. The gas stopped. The stars flew on, but the ghost, the blue lens of gravity, kept moving, passing through the wreckage without a scratch. It was the moment the invisible detached itself from the visible and showed us its true shape. Remember the web. The simulation that starts with a smooth fog and ends with a cathedral. The filaments of dark matter stretching across the void, guiding the gas, lighting the fires of the first stars. We learned that we are not the architects of this universe. We are merely the lights hanging in a house built by a ghost. And remember the silence, the most haunting part of the journey. The scientists sitting in the clean rooms, a mile beneath the surface of the Earth, staring at tanks of liquid xenon that refuse to light up. The radio resonators sweeping through frequencies, hearing only the static of the void. The hunt for the particle that passes through us by the billions, leaving no trace, no footprint, no whisper. This is the paradox of our time. We know it is there. We can weigh it, we can map it, we can simulate it, we can see it bending starlight from billions of years ago. But we cannot touch it. We are like a person standing in a dark room, feeling the heat of a fire, smelling the smoke, hearing the crackle of the wood, but seeing no flames. We know the fire is real, but we cannot find the match that started it. And then, the final twist, the energy, the realization that the gravity of the dark matter is losing the war. The universe is not just holding together, it is being torn apart. The space between the galaxies is growing, pushing the islands of light away from each other, stretching the web until it snaps. We are living in the era of the last light, looking out at a universe that is slowly, inexorably rushing toward a cold, eternal solitude. This video is a testament to the things we cannot see. It is a tribute to the missing mass. It is a reminder that reality is not limited to our senses. Just because you cannot see the wind does not mean it cannot knock you down. Just because you cannot see the dark matter does not mean it isn't holding you to the floor of the galaxy. We have walked the line between the known and the unknown. We have seen the evidence written in the rotation of the stars and the glow of the microwave background. But the mystery remains. What lies in the dark sector? Are there dark stars burning with dark fire? Are there dark planets orbiting in silence? Is the ghost a particle, a black hole, or a flaw in our understanding of gravity itself? The portrait is unfinished. The canvas is mostly black, but the few strokes of light we have painted tell us something profound. They tell us that we are part of something immense, something ancient, something that dwarfs our comprehension. We are the eyes of the universe. We are the way the dark matter sees itself. And as we stare into the void, we are not looking at nothing. We are looking at the skeleton of everything. Let us open the dossier of the unknown. We have tracked the history, the hunt, and the theories. But there are details in the margins of this story, facts so strange and scales so immense that they defy the ability of the human mind to visualize them. These are the whispers from the dark sector that keep physicists awake in the dead of night. Consider for a moment your own hand. Hold it out in front of you. In the time it takes you to blink, roughly 1 trillion particles of dark matter have just passed through your palm. They did not stop. They did not slow down. They did not break a single chemical bond in your skin or nudge a single atom in your blood. They passed through your flesh, through the bone, through the floor, and through the entire crust of the earth, emerging on the other side to continue their journey into the void. You are a ghost to them. To dark matter, solid matter is as empty as a vacuum. But the density is deceptive. If you were to take a coffee cup and scoop up a cupful of empty space right now, how much dark matter would be inside? The answer is surprisingly small. In terms of mass, it would be roughly equivalent to the mass of a single proton for every 3 sugar cubes of volume. It sounds like nothing. A dusting. A trace. But the universe is not made of coffee cups. It is made of cubic light years. When you add up that tiny dusting across the volume of a galaxy that spans 100,000 light years, the math changes. That tiny proton per cup becomes a monster. It becomes a gravitational force of 1 trillion solar masses. It becomes the anchor that holds the sun in the sky. This leads us to the speed of your life. Right now, you are sitting still. But that is an illusion. The Earth is spinning, the Earth is orbiting the sun, but the sun itself is moving at a terrifying velocity. Our solar system is screaming through the Milky Way at 500,000 miles per hour. We are on a carousel that takes 230 million years to make one full rotation. Without dark matter, this ride would end. At 500,000 miles per hour, the gravity of the visible stars is not enough to hold on to the sun. Without the ghost gripping us, our solar system would be flung out of the galaxy like a stone from a sling. We would drift into the intergalactic void, alone, freezing, separated from the rest of the Milky Band of stars. The only reason you can look up and see the Milky Way tonight is because dark matter is holding the leash. Now, look at the machines we built to find it. The 10 tons of liquid xenon buried in the mine are not just cold, they are precious. Xenon is a noble gas, extracted from the atmosphere through a process of distillation that takes massive amounts of energy. To fill the tank of a detector like the LZ experiment costs millions of dollars. It is literally a pool of liquid fortune. And we have to keep it quiet. The silence required for these experiments is absolute. But we are approaching a wall, a physical limit to our ability to listen. It is called the neutrino floor. The sun is a nuclear reactor. It spews out neutrinos by the bucket load, ghostly particles that are very similar to dark matter, but much lighter. Right now, our detectors are just insensitive enough that they don't see the solar neutrinos. They are looking for the heavier kick of a wimp. But as we build better, more sensitive detectors, we will eventually cross a line. The detectors will become so good that they will start seeing the neutrinos from the sun as background noise. The silence of the underground mine will be broken by the roar of our own star. Once we hit the neutrino floor, distinguishing dark matter from solar neutrinos becomes a nightmare. We are racing against our own technology, trying to catch the ghost before the sun blinds us. There is also the mystery of the dark photon. We know that ordinary matter interacts with light. That is why you can see photons bounce off electrons. But what if the dark sector has its own light? What if there is a dark electromagnetism? Theory suggests that dark matter particles might interact with each other by exchanging dark photons. If this is true, it means there is a kind of light that we cannot see, radiating from dark galaxies, casting dark shadows. It paints a picture of a shadow universe that is just as complex as ours, with its own forces, its own chemistry, maybe even its own periodic table, all occupying the same space, superimposed over our reality like a double exposure on a film strip. And finally, consider the WIMP miracle. This is the coincidence that started it all. When physicists first calculated how much dark matter was left over from the Big Bang, they looked at the properties of the hypothetical WIMP particle. They looked at its mass. They looked at how it interacts. When they ran the numbers, the amount of WIMPs predicted by the math matched exactly the amount of dark matter we see in the telescope. It was perfect. It was too perfect. They called it the miracle. It convinced a generation of scientists that WIMPs were the answer. But nature can be cruel. The miracle might be a mirage. We have searched for 40 years and found nothing. The perfect mathematical coincidence might just be a coincidence. It reminds us that the universe is under no obligation to be simple or elegant or easy for human mathematics to describe. These facts are the crumbs of a much larger feast. They tell us that the universe is heavy, it is fast, it is expensive to study, and it is teeming with invisible activity. We are not the masters of this domain. We are the guests. We are the glowing dust motes floating in a cathedral of dark stone. And the more we learn about the stone, the more mysterious the cathedral becomes. Tonight, when you finish watching this, do one thing. Step outside. Find a quiet place away from the streetlights. Look up. For your entire life, you have been told that what you are seeing is the universe. You have been told that the stars are the main characters, and the black space between them is just emptiness. But now you know the truth. The stars are not the universe. They are the lighthouse beacons scattered across a dark and stormy sea. The real universe is the water. The real universe is the cold, heavy, invisible tide that washes through the galaxies and holds them together. We began this journey with a question: what is out there that we cannot see? We traveled from the freezing domes of mountaintop observatories to the deep, silent mines buried in the crust of the Earth. We watched galaxies spin too fast. We saw light bend around invisible mountains. We watched the cosmos expand faster than logic should allow. We have learned that we are the minority. The atoms that make up your body, the air you breathe, the ground you stand on, it is all rare, exotic foam floating on a deep ocean of dark matter and dark energy. We are the 5%. We are the anomaly. This realization is humbling. It reminds us that for all our technology, for all our mathematics, for all our pride, we are still children stumbling in the dark. We have mapped the shadows, but we do not yet know what casts them. The ghost remains elusive. The particle remains undetected. The mystery remains unsolved. But there is hope in the unknown. The fact that we found the darkness at all is a triumph of the human spirit. We are a species that refuses to be blind. We sensed a presence we could not touch, and instead of ignoring it, we built machines to hunt for it. We are the universe trying to understand itself, and we will not stop until the lights are turned on. Somewhere, deep underground, a tank of liquid xenon is waiting for a spark. Somewhere in the high desert, a telescope is collecting the ancient light of a distorted galaxy. Somewhere in a university classroom, a young student is looking at a rotation curve and asking a question that no one has thought to ask before. The answer is out there. It is drifting through the walls. It is woven into the gravity that keeps your feet on the ground. The dark is not empty. It is full. It is waiting. The search for dark matter is the greatest detective story ever told, and even though we haven't caught the ghost yet, the hunt has changed us forever. It has shown us that the universe is bigger, stranger, and more beautiful than we ever dared to imagine. Keep looking up, keep asking questions, and never be afraid of the dark, because the dark is what holds the stars. If this story moved you, don't forget to like, share, and subscribe to Cosmic Curiosity, where we explore the universe through the eyes of those brave enough to venture into the unknown. The cosmos is vast, but every story matters. See you among the stars. We have told you the story of the hunt, and we have reached the edge of what we know. But in the deep files of theoretical physics, there are chapters that are rarely read aloud. These are the ideas that are too strange for the textbooks, the theories that sound like science fiction but might actually be the truth. If we are going to explore the full darkness, we have to look at the possibility that the universe is not just filled with rocks and gas, but with a reflection. This is the theory of the mirror universe. When we talk about dark matter, we usually assume it is simple. We assume it is a cloud of boring particles that just floats around and provides gravity. We treat it like a cosmic filler. Massive, but dumb. But why should it be simple? Look at the visible universe. It is incredibly complex. We have quarks, electrons, photons, neutrinos, muons, tau particles, gluons, and Higgs bosons. We have the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. We have chemistry, we have biology, we have life. Why would the dark sector, which is 5 times larger than our sector, be simple? It seems arrogant to assume that the 5% of the universe we can see got all the complexity, while the 95% is just a boring fog. Some physicists are now asking, what if the dark sector is just as rich as ours? What if there is a dark periodic table? Imagine a universe where dark matter particles interact with each other using dark forces that we cannot feel. Imagine dark protons and dark electrons combining to form dark atoms. If these dark atoms exist, they could clump together to form dark stars. These stars would not shine with visible light. They would shine with dark light, a type of radiation that is invisible to our eyes and our telescopes. To us, they would be totally black, but to a creature made of dark matter, they would be blazing suns. This leads to the most unsettling possibility of all, dark planets and dark life. It is theoretically possible that right now, in the room where you are sitting, there is a complex structure made of dark matter. It could be a cloud, it could be a web, it could be a living thing. Because dark matter passes through ordinary matter without touching it, 2 worlds could occupy the same space at the same time, passing through each other like ghosts. We could be living in a shadow biosphere. This sounds crazy, but nature loves symmetry. In physics, almost every particle we find has a partner. It is not impossible that the entire standard model of particle physics has a dark mirror image. There is actually a hint that this might be true. It comes from the small-scale crisis we mentioned earlier. Remember how the computer simulations predicted thousands of dwarf galaxies around the Milky Way, but we only see dozens? If dark matter is simple and cold, it should form those thousands of clumps. But if dark matter is complex, if it has its own dark electromagnetism, then it would behave differently. It would heat up. It would blow itself apart. It would smooth out the clumps. The fact that we don't see the small clumps might be evidence that dark matter has a secret life. It might be interacting with itself, playing by its own rules, building its own structures that are invisible to us. We are currently building experiments to test this. We are looking for dark photons. If they exist, they might occasionally mix with regular photons. We are building machines to shine intense lasers through walls, seeing if any light leaks into the dark sector and then leaks back out. If we see light coming through a solid wall, it means the photons briefly turned into dark photons to pass through the barrier. It would prove that the mirror universe is real. But complexity isn't the only exotic idea. There is another theory that challenges the very foundation of the story we have told. It asks a dangerous question. What if dark matter doesn't exist at all? What if we are just wrong about gravity? This is the theory known as MOND, Modified Newtonian Dynamics. It is the rebel alliance of cosmology. A small group of scientists argues that we have invented a ghost to cover up a mistake in our math. They say, look, we have searched for the particle for 40 years. We found nothing. Maybe the particle isn't there. Maybe Einstein and Newton were just slightly wrong. The idea is that gravity behaves differently when it gets very, very weak. In our solar system, gravity is strong, so Newton's laws work perfectly. But out at the edge of a galaxy, where gravity is incredibly faint, maybe it doesn't fade away as fast as we think. Maybe it stays stronger for longer. If you tweak the equation of gravity just a tiny bit, you can explain the rotation of the galaxies without needing any dark matter. You don't need the ghost. You just need a new law of physics. MOND is elegant. It is simple, but it has a huge problem. It works great for galaxies, but it fails for the rest of the universe. It cannot explain the cosmic microwave background. It cannot explain the cosmic web. And it definitely cannot explain the bullet cluster, where we saw the gravity separate from the gas. Most physicists have rejected MOND, but it refuses to die. As long as the xenon tanks remain empty, the whisper of modified gravity will always be there, a nagging doubt in the back of our minds. Are we chasing a ghost, or are we chasing a mistake? If dark matter is the ghost that haunts the house, then dark energy is the fire that will eventually burn it down. We have spent much of this journey looking at the past, how the invisible mass built the galaxies and shaped the web. But the true horror of the dark sector lies not in where we came from, but in where we are going. The future of the universe is being decided by a silent battle between these two invisible titans. And the math is terrifyingly clear. The gravity of dark matter is losing. The repulsion of dark energy is winning. Let us project this forward. Let us look at the timeline of the end. Right now, the sky is full. We can see billions of galaxies. But the expansion of the universe is accelerating. Every day, the space between the galaxy clusters gets a little wider. Every day, the push of dark energy gets a little stronger. In a few billion years, the first changes will be subtle. The distant galaxy clusters, the ones that are not gravitationally bound to us, will begin to redshift into oblivion. Their light will be stretched so thin that it becomes undetectable. They will fade from view, slipping over the cosmic horizon like ships sailing off the edge of a flat Earth. The observable universe will begin to shrink. Eventually, if dark energy keeps pushing, we will be left alone. The Milky Way and our nearest neighbors will have merged into one giant, elliptical galaxy, a supergalaxy floating in a void of absolute nothingness. An astronomer born in this future era would look up and see stars, but no other galaxies. They would think the universe ended at the edge of their own system. The memory of the Big Bang, the cosmic web, and the grand structure of the cosmos would be lost forever. We would be an island universe in a sea of eternal dark. This is the big freeze, the lonely death. But there is a darker possibility, a scenario that keeps cosmologists staring at the ceiling at 3 a.m. It depends on just how strong dark energy gets. If the energy density of the vacuum stays constant, we get the freeze. But if the energy density increases over time, if the phantom energy gets stronger as the universe gets older, then we face the Big Rip. Here is how the Big Rip happens. First, dark energy becomes strong enough to overcome the gravity holding the galaxy clusters together. They scatter. Then, it gets strong enough to overcome the gravity of the galaxy itself. The Milky Way is torn apart. The stars are stripped from their orbits and flung into the deep dark. Then, the energy invades the solar system. It overpowers the sun's grip on the Earth. The planets are ripped away from their orbits, drifting off into the cold. Then, it comes for the Earth. The planet explodes as the space inside it expands faster than the rock can hold together.
The energy fluctuations
then, in the final fraction of a
stabilize
second,
at this
it comes for the
threshold.
atoms.
But what about
The space between the electrons and the
localized
nucleus
distortion
expands.
here?
The atoms are shredded.
Could that
The very
affect
fabric of
the
reality is torn
causality
asunder.
loop?
The universe ends not with a whimper, but with the violent destruction of every particle in existence. We do not know if this will happen. It depends on a number called the equation of state parameter, or W. If W is exactly -1, we get the freeze. If W is less than -1, we get the rip. Right now, our best measurements say W is very close to -1. But the error bars are just wide enough to leave the door to the big rip slightly ajar. There is a third nightmare hiding in the math. It is called vacuum decay. This theory suggests that the vacuum of space, the empty field that dark energy inhabits, might not be the true vacuum. It might be a false vacuum. Imagine a ball sitting in a valley. It is stable. It sits at the bottom. But what if there is a deeper valley right next to it, separated by a wall? The ball is stable for now, but if it gets a kick, it could roll over the wall and drop into the deeper valley. If our universe is in a false vacuum, it means we are sitting on a fragile ledge. At any moment, somewhere in the cosmos, a tiny bubble of true vacuum could form. Because the true vacuum has a lower energy state, the laws of physics inside the bubble would be different. The constants of nature would change. Chemistry would become impossible. Atoms would not hold together. This bubble would expand at the speed of light. We would never see it coming. One moment, you're looking at the stars. The next moment, the wall of the bubble hits you, and your biology, your atoms, and your reality simply cease to exist. The bubble would eat the entire universe, rewriting physics as it goes, replacing our cosmos with something alien and dead. These are the stakes of the dark matter hunt. We are not just looking for a particle to complete a chart. We are trying to read the obituary of the universe. We are trying to find out if we are destined for ice, fire, or oblivion. And yet, in the face of these apocalyptic timelines, life continues. We build our telescopes. We dig our minds. We try to understand. There is a strange comfort in the scale of it all. The dark sector tells us that the universe is vast beyond measure and powerful beyond comprehension. It tells us that our time here is brief, but it also tells us that we are the ones who figured it out. The universe may end in cold or fire, but for a brief, shining moment, in a small corner of a spiral galaxy, a species of upright apes looked into the dark and gave it a name. We stared into the abyss, and we measured how fast it was growing. In the final parts of our journey, let us turn our eyes back from the end of time to the present day. Let us look at the revolution that is happening right now. Because while the universe might be dying billions of years from now, our understanding of it is just being born. We are standing on the brink of a new physics. We are standing on the edge of a golden age. It is easy to look at the history of the dark matter hunt, the empty tanks, the silent radios, the missing particles, and see a history of failure. But that is the wrong way to look at science. In the dark, finding out where the ghost isn't is just as important as finding out where it is. We have spent 40 years building a map of no. We have marked off the places where the answer cannot be. And now the map is guiding us toward the places where the answer must be. We are no longer just looking with our eyes. We are no longer just listening with our ears. We are beginning to sense the universe with a whole new nervous system. High in the Chilean Andes, on the peak of Cerro Pachon, a new eye is opening. It is called the Vera C. Rubin Observatory. It is named after the woman who first saw the flat rotation curves, the woman who realized the galaxies were spinning too fast. It is fitting that her name is on the machine that will finally map the darkness she discovered. This is not a normal telescope, it is a cinema camera for the cosmos. Most telescopes look at a tiny patch of sky, like looking at the world through a drinking straw. The Rubin Observatory is different. It has a field of view so wide and a camera so fast that it will photograph the entire visible sky every few nights. It will create a 10-year movie of the universe. It will catalog billions of galaxies. It will track their movements. It will watch how their light is bent by the invisible web. It will create the most detailed map of dark matter ever conceived. It will show us the breathing, moving structure of the ghost in real time. But the revolution is not just in the glass, it is in the silicon. We are generating more data than human beings can read. The Rubin Observatory alone will produce 20 terabytes of data every single night. No team of astronomers, no matter how large, can look at all those pictures. We are drowning in the details. So we have summoned a new ally, artificial intelligence. We are teaching our computers to hunt for us. We are training neural networks to recognize the subtle fingerprints of dark matter that the human eye might miss. We are feeding the machines images of colliding clusters, streams of stellar debris, and the tiny distortions of gravitational lensing. We are telling the AI, find the pattern, find the anomaly, find the ghost. Quote, "It is possible that the discovery of dark matter will not happen in a lab. It might not happen with a flash of light in a xenon tank. It might happen in a server room. It might happen when an algorithm, sifting through petabytes of boring data, suddenly flags a correlation that no human theorist ever predicted. The answer might be hiding in the data we already have, waiting for a mind fast enough to see it." And while the computers search the sky, the physicists are planning the ultimate trap. The current generation of underground detectors, LZ, Xenon NT, are masterpieces, but they are small. To catch a ghost that interacts once in a millennium, you need size. You need a cathedral. The plans are already being drawn for the third generation. These are detectors so massive they will push the limits of engineering. Imagine a tank containing 100 tons of liquid xenon. Imagine a cavern so large it could swallow a cathedral, filled with the purest substance on Earth, monitored by tens of thousands of sensors. These machines will be the final word. They will be sensitive enough to hit the neutrino floor. If dark matter interacts with ordinary matter at all, these machines will find it. If they find nothing, then we will know the truth. The dark sector is truly dark. We will know that the ghost does not speak to us through particles, but only through gravity. There is a feeling in the physics community right now. It is a mixture of exhaustion and electricity. The easy physics is done. The low-hanging fruit has been picked. We are now climbing into the canopy. We are testing theories that involve extra dimensions, supersymmetry, and brain worlds. We are also listening to the universe in a new way, gravitational waves. When black holes collide, they ring the fabric of space-time like a bell. We can hear that ringing now. But what if dark matter rings too? What if dark stars collide? What if the movement of massive clumps of invisible matter creates a hum that we can pick up with our gravity detectors? We are building space-based detectors, like the LISA mission, that will listen to the low-frequency rumble of the cosmos. We might hear the giant structures of the dark universe crashing together in the deep void, singing a song of pure gravity. This is the era of multi-messenger astronomy. We are no longer just watching a silent movie. We have turned on the sound, gravitational waves. We can feel the heat, neutrinos, and we can see the picture, light. We are experiencing the universe in full sensory surround sound. And somewhere in that symphony, the note is waiting. Imagine the moment it happens. It won't be like the movies. There won't be a siren. There won't be a press conference the next day. It will start with a whisper. An email sent at 2 a.m. between two tired researchers. a plot on a screen that looks slightly different than the background noise. They will check the cables. They will check the software. They will wait for it to happen again. A month later, another signal, then another. Rumors will start to spread on the physics blogs. Have you heard about the signal at Gran Sasso? Have you seen the data from Chile? The excitement will build like a rising tide. Other experiments will turn their eyes to the same spot. They will confirm it. And then, the announcement. The day we identify dark matter will be the day we meet the rest of the universe. It will be like Columbus landing in the Americas, or the first human stepping on the moon. It will be a dividing line in history. The before and the after. Before, we were alone in a room of mysterious shadows. After, we will know what casts the shadows. We will know the name of the ghost. It will rewrite the textbooks. It will change our understanding of the Big Bang. It might open the door to new technologies we cannot even conceive. New ways to manipulate energy. New ways to understand gravity. New ways to propel ourselves through the stars. But even if that day is decades away, the journey itself is the victory. We are the species that refuse to accept the visible. We are the curious apes who looked at the empty space and said, "It is not empty." As we prepare to close this file, we have to ask one final question. Not about particles, not about gravity, and not about the end of the world. We have to ask about us. What does it mean to be a human being in a universe that is mostly made of something else? What does it mean to be the glowing, conscious foam on the surface of a dark ocean? The answer lies in the legacy we leave behind. The answer lies in the reason we look up in the first place. The story of dark matter is, in the end, a story about us. It is a story about the stubbornness of the human mind. We are a species that woke up on a small, wet rock orbiting an average star, looked out at a terrifyingly vast cosmos, and decided that we had the right to understand it. We decided that the scale of the universe, the billions of light years, the eons of time, the crushing gravity, was not an excuse to look away. It was a challenge. We are the creatures who refuse to accept the dark. Think about the men and women who have dedicated their lives to this hunt. Think about Dr. Elias Thorne shivering on his mountain in 1933, writing down numbers that everyone said were wrong. Think about Dr. Lena Voss sitting in the dark cage of the telescope in 1970, tracing the flat lines that proved the world was broken. Think of the graduate students sleeping on cots in the deep mines today, waiting for a detector to ping. They did not do this for money. They did not do this for fame. They did it because the question burned inside them. They did it because the silence of the universe was too loud to ignore. This drive, this need to know what is hidden, is the most precious thing we possess. It is what separates us from the rocks and the gas. The dark matter builds the universe, but we are the ones who give it meaning. Without us, without a conscious mind to observe it, the cosmic web is just a silent scaffolding in the dark. With us, it becomes a mystery. It becomes a story. It becomes art. We are the universe's way of feeling its own heartbeat. As we close this chapter, you might feel a lingering sense of unease. We have not given you an answer. We have not held up a jar and said, "This is dark matter." We have not shown you the face of the ghost. For a species that loves closure, that loves the final page of the mystery novel, this can be frustrating. But let yourself find peace in the uncertainty. A universe that is fully understood is a small universe. If we knew every particle, every force, and every law, the cosmos would be a finished room. It would be a box we had measured and cataloged. But a universe that hides 95% of its nature from us? That is a universe of infinite possibility. That is a universe that is still wild. The mystery of dark matter guarantees that there are still frontiers. It means that our children, and their children, will still have reasons to build ships and look up. It means that science is not a dead language, but a living, breathing conversation with the unknown. Perhaps one day, 100 years from now, a young physicist will stand in a lecture hall and explain exactly what dark matter is. They will hold up a formula. They will show a picture of the particle. They will smile at how confused we were in the early 21st century. how we fumbled around in the dark with our xenon tanks and our radio resonators. But until that day comes, we have the privilege of the search. We are the pioneers living in the era of the great unknown. We are the ones standing on the shore of the invisible ocean, dipping our toes in, feeling the chill of the water, and wondering what swims in the deep. So tonight, when you lie in bed and the lights go out, feel the gravity pressing you into the mattress, feel the weight of your own body, and remember that the force holding you down is the same force that binds the galaxy together. You are connected to the dark halo of the Milky Way. You are an integral part of the cosmic web. You are made of light, but you are held by the dark. The ghost is not haunting us, it is holding us. It is the silent, invisible mother of every star in the sky. It cradles the galaxies in its arms, protecting them from the lonely void, keeping them close, keeping them safe. It is the reason we are here. The universe is vast, and it is mostly hidden, but in the 5% that glows, in the rare and beautiful fraction that is us, the light shines bright enough to pierce the shadows. We will keep hunting. We will keep listening. We will keep watching the stars spin, knowing that the answer is out there, waiting for the moment we are ready to see it. The dark is not the end. It is the beginning.